everybody. This is section 1.3. But first we're going to do a quick review of simplifying square roots. And this is absolutely something that they will test on the Keystone exam. So it'll be included there. And simplifying a square root is different than estimating it. You know what I mean? If you are asked to estimate the square root of 27, estimate means like you would want to round it off to a certain decimal place. That's estimating. And the square root of 27 would be 5 point whatever. It'd be 5 point something. But simplifying square roots is a different story. Now I'm going to go through, and this is hopefully all a reminder anyway, a review of old stuff anyway, but I'm going to go over two basically different approaches. But even aside from those two approaches, a lot of calculators, especially if they're in the right mode, can simplify square roots for you. So, like right now in 2019, we have like these yellow calculators in class, and they absolutely, if they're in a mode called math print mode, whatever that means, but if they're in that mode, they will simplify square roots for you. But anyway, a couple quick important properties of square roots, or really any roots, but let's just, never mind, just going to focus on square roots right now. There's certain properties that they have, just things that are true about square roots. And if you have the square root of something times something, the square root of xy, that can be rewritten as like two separate square roots multiplied together. You can separate this into the square root of x times the square root of y. Similarly, you can take the square root of x over y, and it's true that you can break it up into the square root of x all over the square root of y. And we can use these properties, or mainly this property, when we're going to simplify a square root like the square root of 27. And this is the method that I tend to prefer. And this board is not calibrated right now. Oh well. So the square root of 27, what we want to do is we want to take 27 and break it up into two factors. And as long as one of those factors can actually, be square rooted, it's not really a good verb, but as long as we can take the square root cleanly of one of those factors, that means we are simplifying the square root. Like we can't cleanly take the square root of 27, but maybe we can take the square root of like part of it. Like is there a part of 27, a factor of 27 that we can take the square root of cleanly? So essentially we're looking for like a perfect square in 27. And remember that the perfect squares include numbers like 1, but that doesn't really count in what we're doing right now. 4 is a perfect square, 9 is a perfect square, 16 is a perfect square, 25, 36, and so on and so forth. So we're looking for all those numbers that you can take a clean square root of. And I'll say this even early on right away. What you want is to find the largest perfect square. So spoiler alert, when you're looking for perfect squares that are factors of 48, there's more than one. There's more than one. but you want to make sure you pick the largest perfect square that there is and break that off as a factor. So essentially, my method is to rewrite 27 as, what's the largest perfect square that's a factor of 27? And it's 9. So I'm going to break it up into the square root of 9 times 3. And then if you utilize the basic property, you can technically break that up, and as it happens, you can do the square root of 9. So I'm going to go ahead and do the square root of 9 cleanly, and that's 3. Now this, unfortunately, I cannot simplify any further. You can't really do anything with the square root of 3. And so once you've done as much as you can, you're done. And so the simplified answer for the square root of 27 is 3 times the square root of 3. And so that's that problem. And so moving on to the next example, the square root of 48, utilizing the same strategy, what is the largest, and again, what is the largest perfect square that's a factor of 48? Because 4 is a factor, but guess what? So is 16. So we're actually going to say that 48 is 16 times 3, which, we can go ahead and do the square. If you want to go all out and now write it out like that, 2 separate square roots, good on you. But ultimately, we're going to be able to do the square root of 16, and that's just 4. Okay? So the final answer, the simplified answer of the square root of 48 is 4 times the square root of 3. Quick little side note, just to kind of add some commentary and some additional notes on especially this last example. I'm going to erase this so I have the room, but you don't need to erase, and you don't even really have to write down necessarily what I'm about to write down. But let's say, as a hypothetical, you didn't really think to find the largest perfect square, and you decided to break off a 4, because 4 is a perfect square that you can take a clean square root of. So you would say 48 is 4 times 12. And so this gets broken up like that, and then the square root of 4 is just normal 2, but the 12 is still in the square root, so it's still the square root of 12. But guess what? Hopefully you're on your toes enough, right, that you see that the square root of 12 can be further simplified. And so the 2 is already kind of on the outside here, and so you drop it down. And then you can break another 4 off of the 12 and rewrite 12 as the square root of 4 times 3. And so the square root of this 4 becomes, watch, another 2 on the outside, and the square root of 3, the 3 in there, it stays the square root of 3. And so out here you have 2 times 2, which is, of course, 4. And so we would still end up with the final simplified answer of 4 times the square root of 3 like we did before. Okay? And so that's my method in a nutshell. Just you want to find the largest perfect square and separate it as a factor and break it up into 2 factors so you can actually take the square root of that perfect square. Another method that you might know of already is to not just break this up once. So let's go back to the square root of 27. I just broke it up one time, and I just made sure that one of those factors was the largest perfect square so you could actually take it. But the other method involves basically breaking this down all the way into like prime factors. And so 27, I could see you taking 27 and well, I don't know if there's any other way to really start, right? So 27 is 9 times 3, and the 3 is prime, so you can't really break that down anymore. But the 9 can get broken down again into 3 times 3. And so basically you have 3 times 3 times 3. And now what you look for is pairs of factors. And so here, look, we have a pair of 3's. And what you do then is you bring a 3 out in front of the square root sign, the radical sign. So again, a pair of 3's means you bring 1 3 out. Now, any singles, like this single 3, stay under the radical, stay in the square root. And so that's that way, for that example, to end up with 3 square root of 3. With the 48, let's say you do 6 times 8. Neither one of those are perfect squares, but it doesn't matter because you're going to keep breaking these numbers down until you end up with all the prime factors you're going to end up no matter what anyway with. That was good grammar, huh? But, so yeah, we might as well start off with 6 times 8. Neither of these are done, The 6 can get broken down into 2 times 3, and now that's done. And the 8 can get broken down into 4 times 2. The 2 is done, that's prime. But the 4 can get broken down into 2 and 2, 2 times 2. And now when you're looking for pairs, I see a pair of 2's right here, so a 2 can come out in front. But guess what? I see another pair of 2's, so guess what? Another 2 comes out, and the only single factor that would stay under the radical is that 3. And of course, that's not the final answer. You could just do the 2 times 2 to make that 4. And so the final answer would be, as we already got before with my other method, 4 times the square root of 3. So 2 methods. One method is just one break, one split, and you just need to make sure that you're going to be able to actually take the square root of one of those factors. And hopefully it's the biggest perfect square factor in there. The other method involves breaking it down all the way USA, all the way to the prime factors, where you look for pairs, and you do it that way. But before we move on to the main course of 1.3 here, section 1.3, just one more reminder that a lot of calculators can do this simplifying for you. Again, the yellow calculators we have here in 2019, if it's in classic mode, it'll give you a decimal approximation or a decimal answer. And if it's in math print mode, it'll give you the simplified answer. So now let's move on to, I guess, the main part of section 1.3, which is about algebraic expressions. Algebraic expressions involve algebra, which basically usually means variables. So an expression that has like operations and numbers and variables. And let's see what happens in 1-3. This should be more review for us. So we're jumping right into some examples. Evaluating algebraic expressions. So here's an algebraic expression, negative d squared minus 4 times the quantity d minus 2c, and we're supposed to evaluate it for c equals negative 3 and d equals 5. So the obvious first move is to just substitute negative 3 in for any c's and substitute or plug in 5 for any d variables. So that's the first move. believe that's it. So negative 5 squared minus 4 times 5 minus 2 times negative 3. Okay, and now you just have to very carefully evaluate this and follow the order of operations, or at least don't break any order of operations rules until you get to a final answer. Okay? Now, if I was going to follow order of operations like religiously, I would do what's in parentheses first, and then kind of like, if I have to start like a new hierarchy within the parentheses, then I have to do that, because within the parentheses we have subtraction, but we also have multiplication. You know what I mean? Or basically, you could think of it as we have multiplication, and it's like negative 2 times negative 3. Like whatever. If you just want to think of it like that way, you totally can. So we have negative 5 squared minus 4, and then 5, you could save the minus, you could save it, and just do like positive 2 times negative 3. And so you could just do 5 minus negative 6. Once again, if you save the minus for one step later, it would be like 5 minus negative 6. Or you could just deal with this minus right now and think of it as a minus 2 times minus 3, or negative 2 times negative 3, which is a positive 6. Either way, you end up with basically 5 plus 6. And again, I guess we're still not done with the parentheses if we're going to follow this religiously. And 5 plus 6 is 11. And next we would do exponents if we were following order of operations. PEMDAS, please excuse my dear Aunt Sally. If we were following it religiously, we would do exponents next. And right now I want to pause with a breath here, just so we can reset our focus, because man, this is very, I don't know, there's a lot of potential here for students to get this wrong and not know what they're looking at right now, okay? Negative 5 squared. What is being squared? Are we squaring the entire negative 5, or are we just squaring 5? What are we doing? I mean, it's not like there's parentheses around the entire negative 5 and then we're squaring negative 5. It looks like we're just squaring the d, and it's negative out in front, and then whatever d is, you're just squaring whatever d is, and d was 5. So again, and like just the way this is written right here, we're only squaring the 5. The negative is kind of like out in front of that. If we were squaring negative 5, then it would be positive 25, but that's not what this is right now. And then why don't I just do the multiplying at the same time? I don't think there's any harm there. And you can think of this as like minus and then 4 times 11, or you can think of it as like negative 4 times 11. Either way, it ends up being minus 44 or negative 44. And so now the final step is to do negative 25 minus 44, and, I don't want to be a hypocrite right now, because you shouldn't do all things in your head, but I'm going to go out on a limb and say negative 25 minus 44 in my head is negative 69. So that should be the final answer to that problem, that evaluate problem. Once again, it's just a matter of plugging in what they're telling you the variables are equal to, and then following the order of operations and just doing it a little bit at a time, very carefully, You know, write neatly, bring your work down neatly and correctly, and just let the problem clean itself up step by step without doing too much at once or too much in your head. Okay? The next problem is about simplifying. And so in this problem, we're going to simplify by basically combining like terms. So hopefully you're not too rusty on what like terms are and how you properly combine like terms in order to simplify an expression. Remember, like terms have to be terms that have the same variable with the same exponent. So not only has it got to be the same variable in the term, but that variable has to have equal exponents. So for example, this 2x squared term and this minus 4x squared term and also this minus x squared term, those are all like terms that we can combine. So when we do that, it's 2x squared minus 4x squared, and then technically the coefficient here is minus 1x squared. And when you combine the like terms, it's still going to end up being an x squared term. The exponent won't change here, okay? We're just adding these terms together. It's not like we're multiplying the terms together or anything. We're just adding or combining the terms. So 2 minus 4, that's negative 2. And then minus 1 again, that should be negative 3x squared. So 2x squared minus 4x squared minus 1x squared should be minus 3x squared. And then the positive 5x and the positive 1x, those can also be combined to plus 6x. And so basically, that's all there is to that problem. You know, you identify any terms that can be combined based on their variable and exponent, and then you just kind of combine, add, whatever you want to think of it as, the coefficients of those terms. One more example. You know, in order to simplify this, first we're going to have to clear the parentheses by doing what property? The distributive property, of course. So again, you're not going to be able to combine like terms until you kind of clear away these bubbles, these parentheses. And so, we're going to be multiplying negative 2 through this pair of terms in that bubble. And we also need to distribute that minus sign, which a lot of people can think of as a negative 1 because they're technically very correct. It's almost like we're distributing a negative 1. Or, I actually think of it as just a minus sign myself, but whatever. And so negative 2, and now remember, distributing is multiplying. So negative 2 times r, well, that's just negative 2r. And then negative 2 times positive s, that's going to be negative 2s. All right? Remember, this is one of those moments where you really have to write neatly, because if you're not careful, s's can look like 5s real fast. And notice how I'm even writing the letters a little bit smaller than the numbers. Writing neatly can help, you know what I mean? And so negative 1, or whatever, just negative of 2r, that's going to be minus 2r. And then the negative of positive 2s, or just negative 1 times 2s, is going to be negative 2s again. All right, and so now that we've cleared the parentheses, now we're going to keep, making sure we can simplify more, or making sure that, there's, we don't want to be done until there's no more simplifying to do. But since I see a couple pairs of like terms, we can keep simplifying. So negative 2r minus 2r, that's going to be negative 4r, right? Likewise, negative 2s and then negative 2s combine to be negative 4s. And that's all there is to that. Yeah, stop. And so that's all there is to section 1-3 for us. Which again also included that whole simplifying square roots review.